Okay, so we're going to jump into goodness of fit. This one gets it's going to get a little esoteric before it gets practical. I feel like I always get these lectures where we go out into a limb, then we come back in. And the reason that we do that is because with this topic, we're going to sort of show what the ideal scenario would be. And it turns out the ideal thing that we want to do is impossible. And the stuff that we want to do comes later because we can't do the ideal thing. So we have to talk about the ideal thing. And that's the esoteric part. But we'll get there together. It will be okay. So goodness of fit. So what are we talking about when we talk about goodness of fit? Okay, it's really about how good is the model in terms of describing the data that we have. Okay, and it's this basic idea that you could have a model that has statistically significant things, looks great, cool odds ratios, tight at confidence intervals, and things that, based so far on everything we've said in the class and all the metrics we've described, looks like a good model. But it actually doesn't really describe the data very well. So you can get significant things, but the model just sort of stinks in terms of actually predicting the outcome, okay? And predicting the probabilities of the outcome. So this could be, think of simple linear regression, where you can have a scatter plot with some points on it, and you draw a line, and the beta for the line is significant. Okay, it's a statistically significant, non-zero slope to that line, and it cuts through your data. But your data might be a very sort of cloud-like, not very tight to the line, right? And it may just sort of not fit super well. And the line fits through the data, and you have a number for the slope, and the p-value is tiny. But it actually may not describe all the variation in your data very well. So you can get the same sort of phenomenon with logistic regression. You fit the model, stuff looks great, except may not be the best model, may not describe the data very well. And so what we're talking about here is, what we mean by fit formally, is that for every observation, in the ideal world, we would really like the distance between the observed data points, the observed outcomes y, and the estimated outcomes yi hat, this is from the model, we'd like them to be 0. We want this is the predicted value and the observed value. And we'd like them to, on average, be sort of close. Right? We want, in general, our model to predict things that are close to the observed data. Okay, so the terms that we are often using in this line of work are lack of fit and good fit. Okay, so lack of fit is evidence of bad fit. Okay, that these distances tend to be big. Okay, that means there's bad fit, that the model is predicting something that's way off from reality, the observed yi's. Okay, and that typically is that we're rejecting some null hypothesis. When we reject the null hypothesis, we say that there's lack of fit. So the null hypothesis is that there's good fit, that there's lack. This is the total weird way as in statistics that we sort of describe things. The null hypothesis typically is that the fit is good, or that there's lack of evidence of bad fit. Remember all this sort of tongue twisting that we do for the null hypothesis, that there's like lack of evidence that this isn't true. And so that's sort of what the idea is for the null hypothesis typically, is that the fit is, that we don't have evidence that the model is bad, and then we call it good fit. I'm writing this all out, this seems like all these double negatives, but this is exactly how it's defined. So I'm just trying to be upfront with it. But generally the null hypothesis is good fit, and that the alternative is that there's a lack of fit. And the idea here is typically when we add more predictors into the model, we usually get a better fit, right? The more terms you add to the model, the more the fit to the observed data goes up. At some point, you add too many predictors and your model is sort of meaningless because you added 500 things to it. So this idea, this idea is used all over the place in linear regression, right? That you're trying to sort of narrow the distance between what the model predicts for the outcome versus the observed data. Okay, so we're going to sort of talk about three approaches to dealing with goodness of fit today. And this first one, the first two are using this idea of the deviance, and we'll talk about what we mean by the deviance. But within that, there's sort of two subtypes. There's deviance is based on something called the saturated model, And we're going to talk about this is the thing that's the ideal, that it's not actually useful or usable in life, in practice. And so we're going to talk about something which is almost as good. It's going to be called the event trials deviance, and it's based on something called the fully parameterized model, and we'll talk about all that. So this is the thing that is what we can use, and this is the thing that we would like to use, but we can't. Okay, so there's things that use, these are the deviance-based approaches. Then there's this totally other thing called the Hosmer-Lemeshow test. Okay, and it's trying to get at the same idea of goodness of fit, but it's using a totally different approach. Okay, and the Hosmer-Lemeshow test is what we'll talk about at the end. And then actually in the literature, this is the thing you see the most, is the Hosmer-Lemeshow test. So sort of two groups of what we'll talk about. Okay, oh, here we go. This is exactly what I just said. Okay, so this is the ideal. We can't do it. And we're going to talk about, for these last two, the ones you can do, which ones are better to use when. The Hosmer-Lemeshow is a more universal test. It has a few limits, and we'll talk about its limits. This one has some limits. So we're going to talk about the event trials and where you can't use it, which it turns out it happens a lot. Okay. So to get to all of that, we're going to have to talk about some notation, okay? And because they all look sort of similar, so I'm going to sort of illustrate the notation so you're not like, oh my God, they all look like Y and P, and then we sort of differentiate them to be able to work through it. Because these quantities are really important to understanding the goodness of fit sort of idea and how all the methods are working. Okay. So here's 4 quantities, and here's some stuff. Here's a 2x2 table, okay? A really, really simple 2x2 table. Here's exposed on the columns, disease on the rows. Here's just some data, okay? Here's 3 lines of data. Let's pretend these are people. Here's the disease status. Here's the exposed status, and we'll talk about, this is supposed to say p hat, okay? So we'll talk about that. But this is supposed to be the lines of data view. And this is the sort of 2x2 table view. Okay, so yi, this is the easy one. These are the observed values of the outcome in your data. Okay, the yi's. So in linear regression, these were continuous. Here, they're essentially your 0, 1 outcomes in your 0, 1 outcomes in your data. Okay, so here yi's are the D variables, right? And so here 1, 0, 1 on the bottom, and the yi's here are summarized as counts, right? So here we have 6 disease exposed and so forth. Okay, so these are the observed values in the data. This thing called p hat, and this is supposed to be a subscript, it doesn't come out so well. Subscript xi's. This is the average values of being diseased and non-diseased in your data at different values of your covariates. Now, what does that mean? So here, in this column of exposed, 6 out of 10, or 0.6, have disease. Okay, so this is like the risk or the probability of disease, or whatever you want to call it. The probability let's call it the probability of disease given you're exposed is 1. You're 1 for exposure. 0.4 is the probability of disease given you're unexposed. Okay, so we call this quantity many, many things, risk, probability, and so forth. So here we're going to just say in a really generic way, it's the observed, it's basically these probabilities at these values of x. So here's the x variable here is we only have one x variable, it's exposure. So at exposure 1, this is the observed probability, and here it is for exposure 0, okay? It turns out, this is also equal to the average value of y, right? Because there's 6 times 1 and 4 times 0 and divide it by 10 and you get 0.6, right? This is sort of this is the mean of all the zeros and ones for this column is 0.6. It's the same thing. So it says the observed average values in your data. The proportion is the mean of the zeros and the ones. Okay, so that's p sub xi here. Okay, cool. So that is this little one here. Okay, so the yi hat are predicted values of y from some model. Okay, This is, again, this had it on the last slide. This is notation we've seen before. This might be, you have, there we go. Okay, well, she does not, I don't have YI hats on here because we haven't actually fit a model. This is, you fit some model with some covariates in your data, to your data, and you make your model predict values of the outcome at different values of X. So just like we have predicted odds ratios, you can use a logistic regression model to have predicted probabilities. That's what the YI hats mean. These are predictions that come from a model. Different models of different covariates are going to give you different predictions, right? That's that's the idea here, is that you fit a model with these two covariates, it gives you certain predictions for people, and you put in another 3 covariates and you get different predictions. These other things are sort of fixed in your data set. The YIs are just what your data is. If you have 200 people in your study, you have 200 YIs. You can get many, many Y hat sub I's depending on all the different models you fit to your 200 data points in your data set. So this thing changes for every model you have. And these, okay, so these, then this other quantity, p hat xi, are essentially estimates of the probability of y from your model given some covariates. Now this is actually very, very similar to the thing I said over here. This is, this quantity up here, the bottom one, the p hat xi, we used this notation for logistic regression. Here it is over here. Okay, this is truly the predicted probabilities from a logistic regression model. I sort of use that language to describe Y hat sub i's, which is a very, very related concept, except that this p hat xi from a logistic regression model is always a probability. Right? You fit a logistic regression model to your 0, 1 data, and it does not spit out zeros and ones. It spits out probabilities. Okay? It spits out 0.6, 0.6, 0.4, let's say, if you fit this model to your data, because these are, the logistic regression model predicts the probability of the outcomes, not the outcomes themselves, right? That's sort of one of the features of logistic regression model. Your data are 0 and 1s, but you have a model that spits out probabilities that sort of on average describes what happens in your population. That's a little different from Y hat sub I, which is actually a model that might, in theory, spit out zeros and ones directly. Our logistic regression model doesn't do that, but this is a theoretical quantity that we might wish to talk about. It's a little bit different. This is, I described this a little bit more like this one. All that's to say is observed data, the observed average value of the data, and this is predicted 0, 1s, and this is predicted probabilities. So these are sort of paired ideas. And we're going to use these 4 ideas to talk about goodness of fit. So again, so this one is a little more theoretical, the Y hat sub i's, and we're going to just sort of dive in with all this. Any questions? I know it's a little tongue twistery, and they all have overlaps in their definitions, so we can come back to it. But does anyone have any questions? Okay, you can shout out, you can raise your hand. I'm approachable. Okay, I promise. Okay, so there's this thing called the saturated model. Okay, a saturated model is a model that is able to generate 0, 1 values. It's a type of logistic regression model that actually can generate 0, 1 values. It's a weird thing because I just said that the logistic regression model only spits out probabilities. But I'll show you what this looks like. It is able to perfectly predict the outcome data. Okay, and so what that means is, if you have a data set with, say, 200 YIs in it, 200 observations, it is able to produce predictions such that the difference between the predictions and the observed value is 0. This is a perfectly predicting model. It produces estimates, and this difference is 0. Okay, and what this model looks like is, it is a model that has as many terms in it as you have data points. So you have 200 observations, you're going to have 200 coefficients in your model. Okay, it's a sort of impractical model. Okay, so here, that's what this is saying here. You have an intercept, and if you have n data points, You have 1 to n minus 1, essentially, the little subscript, should be a little j equals 1 over here. You basically have n minus 1 dummy variables and then an intercept, or n total terms. And this is a model that exactly is able to, if you fit as many terms in your model as you have people in your data set, your model will exactly predict the outcomes. Okay? It will be beautiful. It will exactly describe the data. But it's a sort of a worthless model. You put as many terms in as points, and it basically fits a term for every single person in the data set. And that term represents that person's value. Okay, so this is a really weird thing. This model is going to spit out predicted probabilities that are actually 0, 1s, or very close to 0 and 1. Normally, predicted probabilities are not exactly 0, 1. It's sort of somewhere in between. But because you put this many terms in the model, it's exactly predicting every point of data. Okay. This is different than a model that, this is different than something that we're going to talk about later, actually. This is going to be the thing that we use in the we're going to call it the fully parameterized model. But basically, this is different than something that predicts the average probability of being a case, this other thing that we talked about. So we're not talking about a model that predicts 0.6 and 0.4. We're talking about a model that predicts 1s and 0s. Okay, that's all this means. So this is a really, really weird model. It looks something like, here's an example of a saturated model. Okay, here's some data. Here's that table, the 6, 4, and so forth. We're going to pretend there's even some strata in the data, let's say. So here's a data set with 40 observations, okay? We have 2 2x2 tables, each has 20 people. 2 strata, C equals 1, C equals 0. The specifics of the tables don't matter at this point. But basically, you got 40 people, okay? You could fit a model with essentially 40 terms in it, and you get something like this. It's really ugly. Okay. Here's our data set. It predicts probabilities that are essentially 1 and 0. Okay, this is our saturated model. It's not exactly 1 and exactly 0, but it's basically 1 and 0. Okay, and what is it doing? It says p hat. This is, again, I'm using the output from the model to actually just manually. I'm using the output statement from the model to generate these. It's predicting that the predicted probability of disease for person 1 is basically 1, and that matches their disease status. Down for these people here, it's predicting their probabilities of disease are 0, and that is these people's disease status. So if you compute the difference between disease and p hat, the predicted probabilities, you get 0. This model basically always spits out the probability of disease, more or less. It's not exactly 0. Okay, so this model is a saturated model. The way I sort of fit it was I said class ID, so every person has an ID variable, and so it's making dummy variables for every ID, and then I say model disease equals ID, so you get a different term in the model for every single person. Don't do this at home. This is not something you should do. This is a not practical sort of model. But anyway, that's what it does. It exactly spits out. It exactly spits out the probabilities of disease as 0s and 1s, essentially these y hat values. Okay, and we're going to talk about some of these deviance statistics in a moment. Okay, but let's just say, the fact is these are practically 0. They're not exactly 0, they're mostly 0. Okay, that's an important piece. The deviance is basically 0. All right, so in summary, this is a model. So the saturated model is this hypothetical thing that exactly describes the data. It nails exactly the data, but it's useless because it has as many terms in it as it has people. It's totally useless. But we're talking about it for a reason, so you'll find out what that is. It's this ideal model that describes the data well that we want to compare to. Okay, so this really says in words, or in more words and formulas, what we just saw on the previous slide, that the saturated model has as many terms and dummy variables as you have subjects. And basically what happens is, here's, for example, it's pretending that dummy variable 2 is 1. So let's pretend this represents ID 2, the second observation. this model reduces to just the logit of P of y equals W2, or not W, sorry, little omega 2. And that's this term over here. And that means that the probability of disease for subject 2 is 1 over 1 plus e to the minus this coefficient. And this will always predict, this is the probability of disease for person 2. This is always true in any logistic regression model. This is just the probability. And because it's a saturated model, it actually is spitting out 0 1s themselves because it's a saturated model. So the probability is going to be 0 1. Okay. If you put this into the likelihood formula for the logistic regression model, the likelihood expression for such models where the probability equals the y's themselves turns out to be 1. So the likelihood of this model, the saturated model, is 1. It has a perfect likelihood of some sort. Its likelihood is always equal to 1. This is going to be important for the deviance statistics. Okay, so this is not that interesting yet. Okay, we have a model that's got as many terms as data points, and it perfectly describes the model. But it's crazy because you would never do this. So the saturated model, but it's just building to this idea of the deviance. Okay, so the saturated model is the best fitting model in the world. It exactly is connecting the dots of your data, and it's got as many terms as data points. Okay, but as we've said, this is not a good model to use, right? It comes at a cost. This is not a usable model when you have 200 observations and 200 terms in the model, and they're not interpretable. They mean person 22. They don't mean, history of alcoholism or whatever the thing that you're modeling is. They just mean person or data point. So that's not useful, okay? But this sort of serves as like a baseline for comparing other models too. Okay, so we don't want to use the saturated model, but what if we can compare our model and how well it fits the data to how well the saturated model fits the data? So we might be interested in it for comparison. And that's this idea of the deviance, okay? And is our model, which is not the saturated model, but may only have 5 terms in it, is it close enough to the saturated model? And if it's close enough, we might say, hey, that's a pretty good fitting model. It's sort of like it's pretty close to how the saturated model fits. And that's the idea of the deviance statistics. It measures how much our model deviates from the best model. Okay, and it's very similar to the likelihood ratio test, right? Because the likelihood ratio test is like, hey, I got a model that's got 2 interaction terms and 1 interaction term. Let's see if one changes relative to the other. Right, that was the likelihood ratio test. Like, let's see whether one model is different from another model. And that's sort of the idea with the deviance tests, except that we're always comparing in the deviance tests to the best model that fits the data really well. Okay, and that's formally this thing here. This is the deviance statistic. It's very, very similar to the likelihood ratio statistic, which I have in a slide at the end of the PowerPoint. We have another slide showing the relationship between the two. But the idea of the deviance is it's a quantity that you can statistically test, and it has a ratio in it that is the ratio of likelihood. So it's very similar to a likelihood ratio test. Okay, in the numerator is the likelihood of the model that you've got, whatever it is. Some model you think it's great, but you're not sure it's great, which is why you're doing this test. Okay, so you have some candidate model, and in the denominator you have the best fitting model. Okay, which might be the saturated model. Okay, and the idea is that the smaller that this quantity is, the better fitting your model is to the best. Your model is close to the best fitting model. Okay, so this thing called the deviance statistic, and the thing is so this is our candidate model that we got our covariates of interest in. But what do we choose for the comparison model is sort of the key piece. And this is the difference between the first 2 deviance tests that I talked about on some slides ago. And the idea here is this thing called there's 2 choices for the likelihood that you might plug into the denominator. One is called the subject-specific deviance, or the subject-specific likelihood. And then one's called the events trials-based one. The subject-specific one is essentially this is the likelihood of this in the saturated model. Okay, so this is the model we were just talking about. You put in the denominator the likelihood of the model where you have as many terms as you got observations, because that is literally the best model. It spits out zeros and ones exactly that match your observed data. Okay? The other option is something called the event trials-based likelihood, or basically it's a model from a fully parameterized model, and we'll talk about what we mean by that. But it's basically got as many numbers of, it's basically every covariate in all of its interaction terms. It's a little different. I'll explain why we're going to use that. So it's a different thing, and we're going to talk a bit about what this is, this likelihood. But this is the likelihood of the saturated model. This likelihood we said was always equal to 1. Okay, it's always equal to 1 because it is the saturated model, which by definition fits the data exactly. It's a little circular. Okay, but that's what it's saturated, fits the data perfectly, always equals to 1. So for this one, the likelihood is usually far less than 1. So the problem is we cannot actually use the test statistic with this likelihood of the subject-specific or the saturated model-based likelihood in the denominator. So even though we would love to use it, we can't. And the reason is, there's a bunch of reasons here. So here's our equation that we just showed on the previous slide. So here's -2 times the log of the likelihood of our sort of the model we care about over the likelihood from the saturated model. This denominator is always equal to 1. Okay, and so it's just -2 times the log of the likelihood of our model. Okay, and this is an expression for that likelihood from our model that we care about. So these 2 bullet points just summarize what we just said here. That this thing is just the deviant. This quantity here, which is just the -2 log of the likelihood of our model, is what the deviant statistic is for any given model. It's the -2 log likelihood. And we call this thing the deviance subject specific, but it's basically the deviance owing to a saturated model. And this is very uninteresting because if the denominator is always equal to 1, that's not telling us anything. So if this denominator is always equal to 1 and of a saturated model, then the deviance statistic is just the -2 log likelihood of your given model. And that in itself is very uninteresting and very uninformative. So there's problems. We're not making an actual comparison if the denominator is always equal to 1. I said in theory we'd love to compare our model to some ideal model, but that comparison is not possible because the saturated model always has the same likelihood. And so it's something we'd like to do, but mathematically we're left by always dividing by 1. And so all we have is our predicted probabilities from our model, and we're not comparing to the observed values in the data, the yi's, and we're not comparing to the saturated model. All this is doing is just the likelihood of the model we have. But the whole point of goodness of fit is that we're comparing how we're doing to some standard. We're comparing our model's predictions to yi's, or we're comparing it to the saturated model. We've got to compare to something. Otherwise, we don't know how well we fit if we can't compare our model to something. So all that's to say is that this quantity is cool, except that this denominator is always equal to 1, and so the thing we wanted to do isn't actually possible. This is really unexciting, I know. It's sort of anticlimactic, because we thought the saturated model would be really good. It would be good, but it's not, because it's always equal to, the likelihood is always equal to 1. So this deviance statistic is in theory good, but is not useful for goodness of fit testing. Okay, and so the ideal isn't possible, so we're going to settle for the thing that's next to the ideal, which is a different deviance statistic that uses a different denominator, and that we think is actually the next best thing. So that's why we're going to talk about it. So I had to show you the thing that's like theoretically we want to do but never works out, and now we're going to talk about the thing that does work out. Okay, and we're going to use something called the fully parameterized model. So the saturated model that we talked about was that first thing. It spits out zeros and ones directly out of the logistic regression model, which is really weird because logistic regression models were not meant to spit out zeros and ones. But what it does is it spits out zeros and ones here and reduces this difference always to 0. Okay, and what we said, it's a really impractical model, and its likelihood is always equal to 1. So we're going to instead compare our model to something called the fully parameterized model. And the fully parameterized model is essentially the most interaction-filled model you can make out of your covariates. Okay, so let's say you have x1, x2, or exposure 1, c2, whatever you want to call it, using our other notation. So you take all of the things, all the predictors in your model, all the basic sort of ingredients, the main predictors in your model, all the covariates, and you make all possible product terms. So if you've got, five terms in your model, it's, age, sex, whatever, alcohol use, whatever it is, you put those in the model. Then you take all the two-way products, all the three ways, up to the five-way interaction term. This is also not a practical model. Not a good idea to have five-way interaction terms, just because what does it mean if it's significant? I don't know. And probably, it's just won't be significant actually. But anyway, the idea is that it's the most interaction-filled model that you can make. So what I mean by that is, let's say you have just two predictors, E and C. Your fully parameterized model is alpha plus beta times exposure, gamma times C, and then delta times E times C. This is literally the most complicated model you can make with the data you've got, okay? This is not the saturated model, right? The saturated model would be as many terms in the model as you have covariates, okay? That would be, not covariates, data, lines of data, right? So if you have 100 people in your data set, you'd have 100 terms in your model. This is the most complicated model you can make with the X variables that you have. Okay, and again, if you have only a binary predictor, then your fully parameterized model is really boring. It's just a term for exposure. That's all you got. So this is not necessarily a saturated model, right? It could be if you can sort of have a very tiny data set, and it could sort of work out. But what's cool is the fully parameterized model completely always predicts the average probability for each combinations of x's. Okay. So what I mean by that is, I'm going to just jump back up here. I think we'll maybe even illustrate it down below. Okay, back up on this slide here. Your model, the fully parameterized model, doesn't spit out the zeros and ones exactly, but for every pattern of covariates, it perfectly predicts the average in that group, the average probability in that group. So, for example, if you had just a model with exposure in it and you fit it to this data, your model would spit out 0.6 and 0.4 for your exposed and unexposed. So here we go over here. So it's actually, your model exactly predicts the average experience of that group. Not the zeros and ones themselves, but it predicts the average in the population of the outcome. So that's the difference between that's what the fully parameterized model does. And we're going to illustrate this with SAS in a few slides, but I wanted to just show what I mean by that. So it doesn't predict zeros and ones. It predicts the average exactly in the data set at the covariates, okay? Because you're fitting as many terms as you have possible products of your variables, and this will always predict the average experience for all combinations of x's. Okay. But not the zeros and ones, average. So, okay, so what I mean by that is here. So if you have, okay, there we go. So one thing that's sort of important to think about is this idea of covariate patterns, which is all the combinations of values of your X variables that you can have. Okay, and this is what the fully parameterized model is going to predict well. It's going to predict the average for every pattern of covariates. SAS calls this thing unique profiles, okay, in the output. What covariate patterns are imagine if you've got a data set with just one exposure, E, okay, and it only takes on the values 0 and 1s, there's only two possible covariate patterns. X is 0, X or exposure is equal to 1 and exposure is equal to 0. The people in your data set only take on two types of X, like across all their X's, they can only be exposed or unexposed. If you've got two covariates, two binary covariates, exposure and confounder, C, then there's 4 possible types of people you can have in your data in terms of the covariates, right? The people that are exposed but a 0 for the confounder, unexposed, 1 for confounder, and so forth. Both 1s, both 0s. So you can have zillions of people in your data set, and if this is all you measured on them, these are the only 4 types of people you really get to observe in terms of their covariates, their exposures. They might have different y's, and the y value, because you have y equals 1 or 0, you can have 8, I suppose, total types of people. But in terms of the covariates, there's only 4 patterns to the covariates. Okay? So the fully parameterized model, if you have a model that's E and C and its product, is going to exactly predict the average y value for all 4 of these groups. Okay, so that's what for every pattern of covariates, it's going to exactly predict the average experience. So if you have data with continuous variables, now you can have more than just sort of a fixed number of groups, right? The number of covariate patterns is going to depend on how many values of the continuous variable that you have. So, for example, if you have just a single x variable in your data set, age, your covariate patterns is the number of distinct values of age that you have, right? If you have integer years of age, and then the number of years you observe is the number of covariate patterns. If you have a continuous variable and discrete variables, then you can have way more covariate patterns, right? You might have 4 times the number of ages in your data set, or whatever it is. So all that's to say is that this gets a little more complicated with continuous variables, that you don't have as many, you have a proliferation of the number of combinations of x's that you have, or these covariate patterns. So this is going to be very important in showing the limitations of the deviance statistic that we're going to talk about, this sort of when you have a continuous covariate. This is just, okay, so we're going to use this terminology, covariate patterns, for the deviance test. We're also going to use it on Thursday for ROC curves. So we're going to use the letter G to describe the total number of possible covariate patterns. So G for this one predictor model is 2, because there's only 2 possible covariate patterns. Here G is 4 covariate patterns. Here it's large, it's as many levels of age that you have. And then here, if you had a binary variable, then it might be 2 times G, from here, right? Where you might have twice as many levels as just a model with just age in it. If you have a binary exposure and age, you might be doubling the number of covariate patterns. All this is to say is that G is just representing the number of discrete types of people in your data. When you have no continuous data, we have no continuous x variables. This is usually small, usually significantly smaller than n, the number of people in your data set. When you have continuous data, you usually have a number of covariate patterns that's almost as much as your n, right? So if you have basically no 2 people in your data set are the same, if you have a bunch of different continuous variables, it's unlikely that you're going to have too many people at the exact same intersection of covariates, right? That's just, the more variables you have, the more continuous variables you have, people get more and more distinct, unique profiles, and so forth. So then usually it's closer to n. And so why are we talking about this? This relates to the fully parameterized model, as I suggested earlier. So given that you have some basic predictors, you can make a fully x1 to xp. In a data set, you can make a fully parameterized model, and it always has as many terms in it as you have unique profiles. Okay, so before I talked about, you have a single exposure. You only measured one exposure, so the most complicated model you can make would have just intercept and exposure. Well, it has 2 terms in it. That's actually the number of unique covariate patterns. You only can have, we just said on the earlier slide, that G equals 2. Similarly, the fully parameterized model, when you have 2, 0, 1 x variables, is just this. This was the fully parameterized model. it's intercept, exposure, C, and then the interaction, 4 terms. Turns out that's also equal to the number of unique covariate patterns. So it turns out, in general, this pattern is the most high-order interaction model that you can make. Also happens to be the number of distinct covariate patterns. So here, if you have 2 binaries, this is going to be 4 types of people. Your interaction model is going to have 4 terms in it. This is just an observation. Yes, question. No. So the question was, is it possible to have the number of the covariate patterns, exceed the sample size? So no, you can never have more intersections of them in your data than you have data of these pieces. You may have some unobserved intersections, right, of your X variables. Like you may literally not have somebody who is, a 99-year-old Hispanic from Alaska with a mohawk, or just, some very, whatever it is, some very rare intersection. That may not occur in your data set, but the number of observed patterns is always less than or equal to the sample size. So this is just an observation that it turns out that the highest order interaction model always has as many terms as the number of covariate patterns. And what happens here is we're going to fit the model with we're going to fit a model that are fully parameterized. And this model, as we said, is essentially, doesn't predict the 0-1 outcomes perfectly. The fully parameterized model always predicts the observed average probabilities in the data perfectly. And that's actually pretty good. That's actually almost as good as predicting the probabilities itself. If you can, on average, predict if you could predict the observed 0-1, you would like to predict the observed 0-1s themselves, but instead the fully parameterized model predicts the probabilities themselves, and that's still really, really good. So we're going to sort of walk through this and make a test statistic out of it and talk about it. So here's the data that we showed before. It's got exposure 1-0, C 1-0, 40 observations. If I fit this model, exposure C and then E times C, that's this, 4 terms. It's got an intercept in it. We get something that looks like this. Okay, you can get some odds ratios, you can get some predicted probabilities. So here you get, this is just from the 2x2 table even. These are the odds ratios. Here's the predicted probabilities on the columns. So here this is 0.6, 0.4, what we saw earlier. In this table it's 0.3 and 0.7. Anyhow, SAS is going to spit out some stuff of interest. This thing, 51.355, is the -2 log likelihood of your model. You can use this for the likelihood ratio test. You can also use it to compute the deviance from the saturated model, because this divided by 1 is that deviance statistic, but we said that's not very useful. Then SAS, if you can spit out this table, and it says deviance 0, 0, 0, 0, it's not very useful, okay? What is this about? Give me a moment, we'll talk about it. So what's interesting about this model? It's not a saturated model, right, which we know. Does not have 40 terms in it. It's 40 observations, doesn't have 40 terms. It's G equals 4. There's only 4 covariate patterns to it, right, as we talked about. There's only 4 levels of C and E. Okay? So this thing is what we're going to call this is the fully parameterized model. Okay, this has as many as all possible terms that it could have given the covariates that we have that we observed. Okay, here's another model that we fed. This model is just E and C, no interaction term. Okay, suddenly there's information here, 3.6961. This is the deviance statistic computed for our model. It's using the -2 log likelihood for our model in the numerator, but in the denominator, is the likelihood statistic from the fully parameterized model. Okay? It's comparing this model that does not have an interaction term to the model that does have all possible interaction terms. Turns out in this case, it's sort of a plausible model. This might actually be interesting to us. If you have 10 covariates, this is going to be a model that has a 10-way interaction, 9-way interaction terms, and all sorts of crazy stuff. And you'd rather not fit that yourself. So what SAS is going to do is it will compare your model to the most interaction-heavy model possible. And it's going to give you this thing called the deviance. We call it the deviance ET because it has to do with events trials data, which we could go into, but I think we may have a slide on it at the end as sort of supplementary. But we call this the deviance ET, and this is the deviance statistic that compares your model to the fully parameterized model, not the saturated model, because the saturated model always has a denominator of 1 for that deviance statistic. And this thing is essentially a likelihood ratio statistic. It's comparing your model specifically to the likelihood of the fully parameterized model. So it's a very, very specific likelihood ratio. Your model not to any model, but to the fully parameterized one. And this is because the fully parameterized model always predicts the observed probabilities in your data set. So the fully parameterized model is always predicting these 0.6s and 0.4s and so forth. Your given model may not. And it's comparing your model to the fully parameterized model. So this sort of makes sense. So if you zoom back out for a moment, we said in one way that the saturated model is sort of as good as it gets. If you've put 100 terms in your model that sort of fits, and you have 100 data points that fits your model exactly. Another way to think of the best model is the model that has as many terms in it as you measured things on in your data set. If I measured 10 things in my questionnaire, the best model, the most descriptive model you could fit would be the one that put all 10 questions in your questionnaire in there, all their interaction terms, and every single term that you could put in your model, you threw it in there. It's an ugly model, but that's sort of the best model that you could have come up with from the stuff you measured. If that makes sense, sort of the intuitive explanation, right? You measured 10 things in your study, you put all of them in the model and all their combinations, and that's your best model for describing the data. It's a totally ugly and useless model because it has a 10-way interaction term and 9 ways and 8 ways and all of that, and it's actually a terrible model, but it's a very good model in terms of predicting the most in your data set, right? It predicts, using what you've gathered, the outcome as best as you can from what you've measured. And what we're doing here is peeling back and saying, well, I got a model that has only 2 terms in it. Can I please compare my model with 2 terms to the 10-term, 10-way interaction sort of Goliath model, and are those 2 meaningfully different? And that's what this deviance statistic is. So we're comparing to sort of a different ideal, which is the most full model that you can make given the stuff that you measured. Okay, and this is what it formally is. This deviance statistic is a chi-square statistic, and the degrees of freedom is the number of terms dropped comparing your model of interest to the fully parameterized model. So in our case, it was just 1 over here because it was we had a model with E and C versus E, C, and then the interaction terms. We had to drop 1 term, and therefore it has a degree of freedom of 1. If you had 10 terms in your model, then the fully parameterized model has a ton of terms in it. It's got the 10-way interaction, it's got all the 9 ways, all the 8 ways, all the 7-way interactions, down to all of the 10 single main effects. It's a huge model with a ton of terms in it. You'd rather not calculate that yourself, so SAS actually spits out the degrees of freedom right over here. Okay, so the number of terms dropped from your model, and that this is essentially a likelihood ratio test, but it's a very specific test of your test to the model that has the most terms in it. And you can sort of eyeball it, that if the ratio of the deviance over degrees of freedom is about 1, then that actually means you have okay fit. That the null hypothesis of good fit stands. It's sort of a non-significant result. So you can sort of just look at this ratio and eyeball it. So there's a big caveat here to this model. Here we go. Involves dogs. I like Google image search, so here we are. We have dogs. This only works if you have a reasonable number of covariate patterns. So if you've got the number of covariate patterns that's very large, so you have a continuous variable. We talked about if you have age and you have now as many observations, you have as many unique patterns of covariates as you have people in your data set, essentially. Then what happens is your fully parameterized model looks like the saturated model, right? If you have as many covariate patterns as people, it sort of means that the most parameterized model has as many terms as people. That sounded really circular, but as you get more and more covariate patterns, you start fitting what essentially becomes a saturated model, and we said that doesn't work. So what happens is this test only works if the number of covariate patterns is pretty small, you don't have lots of unique intersections of continuous variables, and you have as many covariate patterns as people. Okay, so this only works if you have essentially a handful or not too many sort of categorical 0, 1 or 0, 1, 2, 3 sort of X variables. If you basically have as many covariate patterns as people, then you can do this because essentially you wind up getting this test that doesn't work, which is the one that's based on the saturated model. Okay, so that's a problem when we have continuous data. So when this doesn't work, we don't use this test statistic based on essentially a likelihood ratio test versus the fully parameterized model. We do something called the Hosmer-Lemeshow test, which we're going to start, but we are not going to finish. So we're just we can pick it up at the beginning of next time. But the Hosmer-Lemeshow test, I'll just say what it does and give you a sense of it. It's actually way more user-friendly. It's going to make so much sense. It's going to make a lot more sense than the last thing we just talked about, which will make more sense when you review it. And feel free to ask questions of me. Okay, so the Hosmer-Lemeshow test also measures how close we are to the average predicted probabilities in our data set. So it's going to say, hey, does your model predict the average experience of people with these covariates? Well, not the exact 0, 1s of people, but the average experiences of people with given covariate patterns. Okay, it has nothing to do with deviance. So this is good because it's going to not be limited by the ways that our deviance tests were. And it's really great when you have many, many, many covariate patterns. So if you have all these unique people in your data set, it's going to be great when you have that many covariate patterns. And it actually thrives when you have a lot. So it's not a very powerful test when you have very few covariate patterns. If you have just 2 variables that are 0, 1, and there's 4 covariate patterns, the test never shows significance. It works very well where the other test leaves off. And I'm just going to throw this on the screen here very, very quickly, and then we'll pick it up next time. The example that we're going to use is sort of a classic example used in many pedagogical examples from Evans County. It's a coronary heart disease study. And here's some model here. And it doesn't matter what model, we just want to know about it. Does this model fit the data well? And here it's got a bunch of variables, it's got age, and we expect that because it has age, let's say age is measured, as it's continuous, it's going to have a lot of covariate patterns and maybe as many unique patterns of covariates as you have people. And we're not going to want to use that deviance statistic. We're going to want to use the Hosmer-Lemeshow test. And basically what it does is it makes a table that looks something like this. It divides your data into groups, into deciles of what's called deciles of risk, and we'll talk about what that means. But basically, it takes your model and predicts for everybody their personal probability of disease. It's like, hey, you're 18. This is your cholesterol level, and this is your covariate. I predict, put it through the machine. I predict your probability of heart disease is 0.2. Okay. I only observed a 0 or 1, right? I'm that person in the data set. I only had a 0 or 1, but the model says, hey, your probability is 0.2. That's how logistic regression works, right? You have a 0 or 1, it predicts a 0.2. But what it does is it summarizes the entire data set. Here in this data set, there's basically 10 times 61, so 609 people are in this data set, essentially. This represents the entire data set, and it looks at how well the sum of those predictions compare to the sum of the observed events. So what this means is, for example, there were 61 people in this lowest decile, and in the 61 people, only 2 of them had heart disease. And I took this, then I took the logistic regression model, and I ran for each of the 61 people, I predicted their personal probability of disease out of the regression model. And I summed those predictions up. And they're going to be tiny because these are low-risk people. There's only two of them had heart disease anyway. And the sum of all of those 61 predictions was 0.94. Okay, and so that is the sum of everyone's prediction. And you do this for every decile, and you say, hey, was the sum of all those predictions different from the observed? So here I saw 2, and I predicted 0.94 in this group of 61 people. Here, this is the high-risk group, and of the 60 people, 29 had heart disease in reality, and the sum of the 60 predictions for those people was almost 29. So you might say, hey, that's pretty good. On average, when I split up the data into this pretty 10-row table, the total of the observed events was very similar to the total of what the model predicted for those very, very same people. Okay, and this is the Hosmer-Lemeshow test. It's going to look at the difference between these two. And if your model's sort of nailing it every time, or on average, hey, look, the model says 29 and I observed 29, that's pretty good. Here I'm only off by 1 on average, 2 versus 0.94, 1 versus 2, 1.96, that's sort of 2. Those are sort of small deviations maybe. And so all this is doing, it's a chi-square test of this table. That's just, hey, on average, how does the model do relative to reality? This is so much more user-friendly than the deviance statistics. And this is the basis of the Hosmer-Lemeshow test, which we'll talk about on Thursday. So thanks.